again, and we looked at this example here. As a second example I will address today. Also we looked at the beginning, at least, from Patankar, talking about finite volume. So now we say again, this overview over CFD is quite okay. Finite difference with Taylor series, finite volume either from variational calculus or from the weighted residuals, where you have more advanced weight functions than just a 0 or 1 as we have it here with finite volume. We looked at a couple of examples, found out linear variation, that's okay. Then you will get the exact same discretization scheme as you would with finite difference if you have constant delta x. But here you will have better bookkeeping, you might say, with a lot of different delta x's here. So you can play around a lot with the location of your layout. It's on an integral version already, so you can do pretty much what you want here. Yeah, maybe we should say something about that. For simplicity and sort of frequently without thinking, what we normally do when we design a mesh is you have one mesh cell here, and then the next one comes here, of course. But it doesn't have to be like that. This is allowed. You have one mesh here, and then you have another one over here. That's not illegal. Although of course you will have trouble connecting these two. So here, typically, what you then could have done was have a third one, something like this. This is still okay. The laws should apply for any control volume. So if they overlap a little bit, so what? That's allowed. Of course, this is much easier because you know the flux out of one cell automatically goes into the next. Not so here necessarily. So here, of course, you will have a lot of interpolation, but it's still allowed. So don't limit yourself that they have to be side by side. No, they don't have to. The equation still applies. It's an integral over any control volume. So you can do actually whatever you want. Of course, we think simple and make them rectangular and nice and put them side by side. So here, yesterday we saw this advection diffusion equation using central schemes blows up. So the remedy was the first order upwind scheme, according to Patankar, which at least gives you more realistic results, although pretty far from what they should have been, since it's only a first order, and also we know that scheme is very diffusive. Here, taken from Patankar, the way he defines false diffusion. Because he, of course, has to admit that his first order upwind scheme is very diffusive. But he doesn't call it false diffusion. He calls it a diffusion which we will actually like to put into the system to make it stable. So I think he calls it a numerical diffusion or something. He didn't call it false. What he calls false diffusion is the grid diffusion. So for example, you have the problem here with no viscosity, the Euler equation, where we now have flow coming in from the left, and here hot temperature or cold temperature, or it could be concentration or whatever. If you don't have any diffusion coefficient, then this difference should be sharp, and it should continue to be sharp when the flow goes. It shouldn't mix. And the same should happen either way you orient that flow. Now for the first order upwind scheme, you will have the correct solution directly. With central scheme, you can forget it. You can't use central scheme with the Euler codes. Then it blows up, as we have seen. So only the advection equation there, it's unconditionally unstable. So then, well, it's possible, but then you have to treat him quite special. We'll see as an example later. So now you take the same problem, but you flip it 45 degrees. So here you will have now the hot side and here the cold side. And the correct solution should still be a sudden jump from here 0 to 100 along this line 45-degree angle. But you see the effect. It is getting smeared out if you look at the different numbers here. So we will have a diffusion effect present here with the first order upwind scheme. So I think I'll call this false diffusion. And yes, it is a diffusion mechanism, quite clearly. So here again, it says that the upwind scheme introduces something artificial diffusion. Not necessarily false, but something that we want to put in there to keep the scheme stable. That's his choice. So now here a comparison of the same test case, a very classical figure. Test case where you check the convective diffusive equation, and you let your unknown go from 0 to 1, and here you play around with different cell Reynolds number, or Peclet numbers, and then play around with different codes. The central difference will be a straight line, varying linearly with the Peclet number. But go outside plus minus 2 and you are really in trouble. Then he sort of blows up, start this oscillating, quite unphysical behavior. The first order upwind is stable for any cell Reynolds number. It was unconditionally stable, but far off what it should have been. The exact should be here somewhere. A hybrid scheme can easily be designed. You use the central scheme if possible, but if the local cell Reynolds number is bigger than 2, you switch to the upwind. But it's not a nice behavior either. We also have some power law, which just for this example, luckily coincides with the exact solution. You have of course other as well. So you have, see from Fetziger, something called quick, quadratic upwind. So a lot of different schemes exist to make this one possible. But say, as a conclusion, the central difference is sort of the best if you are able to use it, if you can keep your cell Reynolds number small. Then he is the most accurate, quite clearly. And unfortunately, if you can't use it, the Reynolds number is too big, okay, then you should really know what you are doing, using quite advanced, then I would suggest, upwind scheme, like quick, muscle. You have several of these advanced upwind schemes. First order upwind should never be used, except maybe as creating an initial field or something. What can we do? Of course, bigger computers, more delta x's and delta y's. That's one option. Also try to avoid any angle between the flow and the grid line. So if you have an angle, it should be 90 degrees. Orient the grid according to the streamlines. Yes, that's an option, depending on the geometry, of course. It can be tricky if you have transient flows. And of course, make the force diffusion smaller than the real viscous diffusion. It's sort of essential, or else you are simulating the wrong Reynolds number. And Patankar says that central differences can't be used. No remedy for force diffusion, gives very unrealistic solutions for hyperclear numbers, that's correct. It can't be used at all when you have zero viscosity, also true. But I don't think that's the entire truth. Remember, you can survive with cell Reynolds number bigger than 2 if you include time. What he has been looking at so far is steady state. But if you add time, then it can be shown that the cell Reynolds number has to be smaller than 2 divided by the Coulomb-Friedrich-Levy condition, where you have a delta t. So you can play around with very small delta t's and still survive. I mean, I once did a DNS on a Cray 2 machine where my cell Reynolds number was around 50. But since it was a DNS, I had to resolve all the turbulent scales, both in space but also in time. So I had to use a very small delta t anyway. So this ratio here turned out to be 1.25. So it was okay. Although my cell Reynolds number was way bigger than 2. This test case that Patankar describes here, you tilt it 45 degrees. That's actually also in the book by Verziger. So as a second example, should be here somewhere. Yeah, it starts here. Another popular test case. So figure 4.7 should then be here. So exactly the same problem. You have a constant velocity field given by the velocity vector at 45 degree angle. So you know the velocity. And then we say I have a concentration here of phi, 1 here, and 0 here. These will now be the inlets. And my equation is only the advective part of the transport here. It's only this one. Velocities are given, they are constant, equal to 1, say. So this is then equal to 0. I don't have any viscosity, hence this gradient should be sharp. So if we test that one, should be here somewhere. Yeah, should be here. So now I have only a case here 10 by 10, and I do this with upwind scheme here, but I also do it with the central scheme. So let's see how this looks. Where is it? I'll run it again here. There we go. this is a solution from the first order upwind scheme. So the ISO lines here now describing the unknown quantity phi, which was 1 here, and then a gradient from 1 to 0, and here 0. And you see really the smearing out is quite strong. With a central scheme, it's actually possible to get this one. I'll come back to that, how this is done. For the smearing out effect, it's just the center profile here. So the central difference scheme actually makes the jump over one cell, as you should, but the upwind scheme smears it out. And here you can push on so many cells as you like. It really doesn't help. Here it was a 10 by 10 case, so if you jump to a 100 by 100 case, where's figure 1? Here. You get the same image, it doesn't help. You still have this smearing out effect from the first order upwind scheme, no matter what you do. This can't really be avoided. But here, it was then possible to achieve the correct solution with the central difference scheme. Although it shouldn't be, because it should then be unconditionally unstable if you sort of program it directly. But let's have a look. So the equation now reads something like this. You have a U. It's a party somewhere.
Party music.
Boring music. And then we choose U equals V equals 1. So it's a very, very simple problem. Taking the central differencing scheme, CDS, what will you get? Well, we can also say here for simplicity, delta x equals delta y equals h, something like that. Then it should be very, very easy indeed to solve this one. You have a delta x, let's see, it should be something like this, u over 2 delta x, phi I plus 1j, minus phi I minus 1j, right? And then you will have the same here, v over 2 delta y, phi I j plus 1, and here j minus 1. And then equal to 0. And this then is a second order accurate scheme, so it equals outer terms of order delta x squared and delta y squared. So solve this one. Well, that's not so funny to write that one on the form phi ij equals to, because phi ij, the center point, doesn't enter the equation. It's not here. So what I have to do to make it run, I had to use actually the let's see, the CDS. I had to use sort of the values that were already known. Now the geometry was so nice, so you know everything here and you know everything here. Then my discretization star, it actually looks something like this around a point ij. You're using these 4 neighbors, but you only use the neighbor point, you don't use the center point. So if you know everything at the bottom and to the left, yes, it's possible to evaluate these two based on the rest. So you can sort of march your solution forward here numerically. by solving this equation system. Of course, also possible here to solve it using a direct method. It's not that tricky. But yes, it was possible. But special care had to be made, since you don't have any on the diagonal. So if you write that one as a matrix system, you're in trouble. The diagonal is 0. Not very numerical methods like that. But of course, the deprogramming, yes, it's possible, of course. You can find the +1 values based on the -1 values all the time. So you can sort of sweep up the solution here in the correct direction. Yes, that's possible. For the upwind scheme, UDS, what will we get? Well, more or less exactly the same, except only one delta x, and you use the center point all the time. Delta y Vij minus Vij minus 1 equals to 0. First order accurate, very easy to program. Write this one on the form Vij equal to, and there you have it. So also he is very, very stable. To find what's going on, to find this diffusion that's not here. I mean, we don't have any diffusion, but for this equation it was present, for this equation it was not. To see it, you find the modified equation for both of them. Finding the modified equation, you had to insert the Taylor series here. You will have the difference between the positive and the negative series. So what will you get here? You can write it up. Phi plus minus 1 equals Phi plus minus delta, say x, phi derivative, delta squared half, phi double plus yada yada yada. So what will you get? You will have you choose delta x here, and then the difference, the center point falls. The next one, he will survive, and you will have two of him. Since you have minus and minus will be plus, so you have 2 times delta x phi derivative, as you should. The next one disappears, he will fall. The third one, he will survive. So you will have something phi 1, 2, 3, a third order term. And the same goes with the y direction. So yes, you get back your original differential equation, and you get a third order term. That's a third order derivative. It's a second order accurate, because here it will be delta x power 3, but you divide by 1 delta x here. So it's a second order accurate. What about this one? Well, here you will have first center point minus the series, center point disappears, and then the first term survives. You will have minus minus becomes plus, so you will have delta x phi derivative, and then this term, he survives, so that's something new. He is going to be negative, so we will have minus delta x square half phi double, and then even higher order terms. So here again the scheme is consistent. The delta goes to 0. You are left with just a derivative, as we should. Also you see it's first order accurate, delta x squared by delta. And last, throw this one on the other side. What do we get? You will get a term looking like plus when you throw it on the other side. So this one will mean phi derivative equals, what will it be, u delta x half phi double, something positive. So there you have your diffusion, the viscosity. And for this example, this one is a constant viscosity, which is exactly what we get. But with the central space scheme, no diffusion whatsoever. I will put up this on the home page so you can find it there and play around with it if you like. Any questions to these? That's okay. So the trouble now, having a flow 45-degree angle on the mesh, it's not fun using upwind scheme. Much more fun using central scheme if you can do it. So that's the problem. Of course, you have more advanced methods with this upwind concept. Here we do it very, very easy. We have the velocity in the x direction, you have the velocity in the y direction. And that is sort of deciding how should we create a derivative here, finding the direction of the flow. But people have been playing around with different systems for many years, trying to find it better. So looking at a real flow problem, and say you have a collocated mesh, so you have all your unknowns here, and say now we want to find what's the derivative on this face here, depending on the flow. Well, if the flow, say, comes in at an angle, something like this, then of course it wouldn't be so very nice just to use this value alone. So to find out what's happening here, you should go in this direction, and then you can interpolate using actually as many points as you like to find out what's happening here. But you should then go in this direction, and that is exactly what people have been trying to do with higher order upwind schemes. Sort of have a region here in this direction, and then interpolating a lot to find out what's actually happening and how it is transported against my cell. So yes, there exists advanced schemes like based on such upwind control volume theory, but a lot of geometry, and in the end they are not so efficient anyway. So I don't think they really have really applies. You have these quick quadratic upwind using 3 points, good enough, I would say. You have also this muscle in several codes now, which is also a little bit more advanced, taking many more points on the upwind side, interpolating nicely, and performs reasonably well. So I won't pursue this theory any further. We should maybe have a look at. Oh, we can wait. We are going to later on, when we start looking at unstructured mesh systems. There we more easily have an option, create grid lines that is parallel with the flow. So, of course, if this is the flow direction, it would be silly to make such a mesh. You will tilt it 45-degree angle. But in a real flow problem, streamline something like this. Okay, create the mesh. Then you would start maybe looking at mesh system, something like this. And then create some mesh, maybe something like this. Which makes it a little bit harder. You can have not 90-degree angles necessarily all around. You can have more than 4 faces. Here is 1, 2, 3, 4, 5 for this cell, and so on. So it's a matter of bookkeeping. But yes, that's absolutely an option. And it is more efficient if you have it alongside the flow lines, the streamlines. Typically what people do here, you simulate first using potential theory. No viscosity, no friction forces. Very cheap solution, it's just a solution actually of the Laplace equation. And then you have the streamline picture, and then you use the streamlines to create the mesh. And then you fire up Navier-Stokes. So that's one way to create a good mesh. Going to totally unstructured meshes directly can be a mess. We will see that later on using just triangles. But one interesting way to handle complex geometries, say something is flowing here over an airfoil or whatever, you create a mesh like this in some layers close to the wall. Maybe not so many layers, 4, 5, 6, up to 10. Just to resolve the boundary layer, because a lot of physics is happening very close to the wall. Here you have the skin friction, the production of turbulence is happening down here. Very important to resolve this one correctly to get lift and drag forces on an airfoil, for instance. But then out here, you can now start using, for example, unstructured mesh systems, whatever system. Can be very big, and so on. That's actually allowed. You can have as big volumes as you like. As I said earlier, the equation still applies for such a mesh system. But clearly, a rectangular cell system, structured mesh system, much faster to solve, easier to program. This system here, tricky, messy, you need a lot of bookkeeping. Typically here you will use pointers to find out where you are inside your matrices for all the unknowns. Can be really messy. An advantage, of course, with unstructured mesh is that you can handle any complex geometry, and also you can stretch your mesh using large cells where nothing important happened, focusing on areas of interest, close to walls, in small nozzles, in a jet, things like that. So we will have a little bit of that later when we jump to finite volume. The next part in this course will now be not finite volume. We will jump to something completely different. So we will now start with multigrid, and then also later look into Krylov methods, going to get gradients. Now we're talking fast solvers. So that was one of the 3 topics that you can choose among. Fast solvers, and then you can choose finite volume, unstructured mesh, and finally you could choose turbulence. One of those 3 you will have to choose on the exam. So here we now start with multigrid. any questions from you? No, that's okay. Let's see, let's just clear up here. Also in the book by Fitzsiger, he also jumps to fast solvers and now the solution of linear equation systems. Now we have seen some of this before already, solving an elliptic equation system. I showed you an example. That was the Laplace equation. Should be here somewhere. Laplace. It was this problem where we could play around with omega, and we had this initial system here, and when you start to simulate, if you just use omega equals to 1, nothing really happens. It's going to take forever to find a solution when you iterate. So the smart thing to do here was using an omega close to 2, 0.97 I think was a good one here. Then he finds the solution fairly fast and fairly accurate. What was interesting here with these old ways of programming using Gauss-Seidel, Jacobi or SOR was when you have the initial state using random. No, not that. Sorry. We used a random generator just to create a crazy initial field like this. And I now use quite high omega. It finds the solution pretty good within 300 iterations, yes. But now, if I go back to omega 1, that is Gauss-Seidel. Well, he will also find a solution, but he's going to take much longer time. But what was interesting with him was the first few steps. So if I now pauses him, and then we run again, where is it? Initial, and then one step. He is very fast at filtering out this noise. One step, two step, three step, and four step. And now he's not so efficient anymore. Nothing much happens anymore from one step, from one iteration to the next. Very little. So now all this high frequent noise has been removed, but now we have a sort of a more low frequent noise picture. And now he's very inefficient, this method. But the philosophy from multigrid now tells the following: use this stupid old method to what he's good at. High frequent noise removing. That's what he's good at. So now we could have taken this image with this nice bumpy noise pattern, transferring it to a coarser grid. Then these bumps will appear more high frequent. And then do a couple of iterations on a coarser grid. So then we could move the solution back to this fine grid. Then we should have a much better image. So that's the philosophy behind multigrid. Transfer your problem to coarser and coarser grids so that the noise appears more high frequent, where we know these stupid traditional classical iteration techniques, Gauss-Seidel, Jacobi, they are very efficient removing high frequent noise. Using the SOR with an optimum omega here would be a very bad idea. If I now go back to 1.97, that was the good omega for solving the problem, but it's not a good omega for removing high frequent noise. See what happens. One step. It actually looks worse. Second, third, fourth, five, and so on. You see, using omega, a high omega, is sort of a balance here between handling high frequent and low frequent noise together. I think if I rotate him, we should be, no, I can't rotate him. I have to crash him first. Okay. He's starting to find a solution here to the left, more or less, and also on the back here, because there we have the Dirichlet boundary condition. We have set this one to be 0 and this one to be 1. So here he can start finding and organizing the solution quite fast. And then that effect will sort of spread out to the domain. And in the end, he will take these two sides here where we have Neumann condition, derivative equal to 0. But still a lot of noise in this picture. With omega 1 or even lower, that would be much more efficient to smooth out the noise. Omega 2/3, 1 step, 2 step, 3 step, 4 step. And now we should actually stop and move the problem to a positive grid, because now he's starting to get inefficient. And this is typically what you do. 2 or 3 iterations on each level and then go to the next level. That's quite efficient. Okay, that was just a visualization of the theory behind multigrid. So we take a break and then we start with multigrid.